How far can you see? Can you see across a lake? Well, this guy did, and that looks good, but this is a bit of a problem. According to some, this view of Chicago should be impossible on a globe-shaped Earth. What are they talking about, and are they right? We'll find out using geometry and Google. Here's the rough distance across Lake Michigan. We'll use kilometers, except when we're using meters. Hey, did you know that they changed the name of the Sears Tower to the Willis Tower? That's not important. The important question is, can the guy see the tower? Two things about this diagram. Number one, that's a pretty dodgy circle. And number two, for simplicity, we'll assume that the guy is holding the camera at his feet. A little bit of math gives you this angle, theta. It's that fraction of a circle because, you know, the Earth, it's pretty big. There's the radius of the Earth right there. Yeah, it's big, but we can cut it with this line. We'll also break theta in half. Hello, phi. Next, let's find length A, the length of that side of the triangle. We also want to find length B, the size of the bulge of water between the man and Chicago. Got it? So again, forgive the dodgy circle, but we agree that length A plus length B must equal the radius of the Earth. Right? And at this point, some viewers see what I'm doing and they're mad. They're very mad. This is a crazy oversimplification. It's a lie. And you're right. About the first half anyway. But this is practice for a more complete derivation to follow. Because we'll need to do math with triangles. Trigonometry. Remember trigonometry? If not, don't worry. Just please agree with me that if we know angle phi, and if we know the radius of the Earth, then we should be able to find side A, the length of side A, that part of the triangle. And we're done, because now we know enough to solve for B, the height of the bulge of water. It is 125 meters high. So this guy has to look over that bulge to see Chicago. And here's an even more oversimplified version of our oversimplified version of the situation. But there's a reason I'm doing it this way, so kind of trust me if you can. Put the camera at your feet and tell me, can you see the building over that water bulge in the middle of the lake? Yes, you can see the top third of it anyway, which is a relief. Only if we look at this picture again, it kind of seems like we can see more than just the top third of the building. The Willis Tower is the tall one on the left. It kind of seems like we see more than just the top third of it. And what about this claim? If you're looking over a 125 meter bulge, that should cover 250 meters of the building. That's 800 feet, not 1800 feet. Okay. All right, we're going to have to get less oversimplified. And let's get rid of this dodgy oval. That's better. Go away. Clean it up. Tilt. Don't fall off. And go over there. You guys still with me? Good, because we're going to get started again by making another triangle. Meet yet another angle. Alpha. The sum of the interior angles is 180 degrees, so alpha plus theta must equal 90 degrees. No, wait a minute. Is this entire video just an excuse to go over high school math? No comment. We want to find distances y1 and x using this triangle, and you guessed it, trigonometry. Now, our final triangle. We made it with the horizon of the guy with the camera. That horizon is perpendicular to the radius of the Earth. And since theta and alpha are complementary angles, we can call theta, theta. But enough about angles. We want h. What is h? H is the height the building would need to be in order to be visible over the horizon. See, h, that's h. And it's different from y too. And we are almost done. But first, we'll have to use trigonometry one more time on this triangle. We already found values for y1 and x. Now we have a value for y2 as well, and that's all fine and good. But that's not what we want. We want h. How can we find h? With this equation. y1 plus y2 equals the radius of the Earth plus h. Both of them are expressions for the distance from the center of the Earth to the top of the building. And we know everything in this equation except h, which means we can solve for h. And that is just under 500 meters, which is great. Except that it's horrible. Uh-oh. Oh no, the Willis Tower is only 443 meters tall. But according to this, it would have to be 499 meters tall in order to be seen. But we can see it. Help! This is unsettling. And we have made it back to the beginning of the presentation. I used 80 kilometers, they used 52 miles, but we got the same ballpark value. You may have heard of a different equation. You may have heard of the formula 8 inches per mile squared, so try it for yourself. Put in 50 miles times 8 inches, divide by 12 to convert to feet. Yeah, you get the same ballpark value, which is great, except that we just disproved the globe, which is troubling. So in order to get our globe back, we'll retrace our steps back here. We found that taking curvature and stuff like that into account, we could not see the building over the bulge. You could not draw a straight line to the building from the guy. You could not poke it with a stick. And the good news is you don't have to. Light is not a straight line. Light is not a stick. Light is a wave. And waves can bend. Waves can curve. That's my whole point here. My goal is to convince you of this, not with more math, but with concepts. With an example, let's think backwards. Let's imagine a very, very loud but completely non-violent, non-harmful, non-injury causing BAM in Chicago. You could hear it miles away, right? Yes, explosions like the eruption of a volcano or a meteor impact or even a man-made explosion can and have been heard hundreds of miles away. You agree with that, right? You agree that you could potentially hear a sound in Chicago. That makes sense. Why does it make sense? It makes sense because we have an intuition about sound traveling in that way. If you're standing behind a house and someone honks the horn in front of the house, you can still hear it. You can hear around corners. Even if the house is made of solid rock or solid water, the sound would get to you. Even if you can't see the car, you could hear the car. Even if you can't poke the car with your straight stick, you could still hear the honk. Sound waves could get there. Yes, sound and light are very, very different. Sound wavelengths are millions of times longer than light wavelengths, but they're both waves. And light flows out of Chicago just like the sound of this BAM flows out in all directions, flowing out of Chicago. They are both waves, and waves are allowed to spread out. And I'm trying to be conceptual here. So if you're okay with sound going over the house, you should be okay with light going over a bulge. And if you want a name for it, you could call it atmospheric refraction. That's the culprit, atmospheric refraction. And atmospheric refraction is a thing. Astronomers use it to find stars. Surveyors use it to stay online. And it's got equations, and they're complicated, and they are waiting for you on Wikipedia. But enough equations. And I'm not trying to name names. I'm trying to see concepts. I'm trying to convince you that light can bend. Well, okay, I like names too. I like this one, Huygens Principle. Each point on a wavefront is the source of a spherical wavelet that spreads out at the wave speed. It's beautiful. Look it up, find animations. It works for all sorts of waves, light waves, sound waves, water waves too, spherical waves, plane waves. It's beautiful. And whether you're talking about refraction or diffraction, and I know that someone is going to accuse me of mixing up my refraction with my diffraction, but either way, if you are a wave, Huygens is your engine. And you don't need to go to Chicago to see it. Here's a simple tabletop experiment first. Does this picture look a little bit reddish to you? Well, that's part of the story. Longer wavelengths bend easier. But you disagree. You disagree. Light travels in straight lines, like this laser, unless it bounces. Or it shines on a wall. Okay, but I can make it bend. I can make it bend with this hair. See that dot on the wall? What would happen if you put a hair between the laser and the wall? This? A shadow? You might think so, but you'd be wrong. It's more like this. Try it for yourself. All you need is a laser pointer and a hair, and you'll see it spread out again. This is the light against the wall. The light blocked by the hair gives you more than just a shadow, because light is a wave. The hair is an obstacle. Like the house. Here it is flattened. The waves bend around the obstacles. Think of water waves bending around an obstacle. Monochromatic light would give us fancy interference patterns, and you can see them. Again, you can see them for yourself with a laser pointer, but that's not the point. The point is that light is allowed to spread out, and the more it spreads, the dimmer it gets. Look at the edge of the pattern. It's dimmer, and that's why you need a fancy camera or a telescope to see Chicago, which you can see with light that makes it curving over the curve of the Earth.